Hello.
So, typical questions or problems that we can decide with these kind of redox equilibrium calculations. There are, for example, nitrogen species, ammonium and nitrate ion, certain pH, and if you can measure the redox potential somehow, that is, if you measure electron activity, then we could decide whether we have ammonium ions or nitric ions, for example, or whether the iron should be present in 3+ or 2+ state. This is easy maybe in aqueous solutions, but less easy if there are precipitates of solid compounds. Do we have carbon in a state of carbon dioxide, or is it organic like methane? Phosphate release from deposits in deep sea where oxygen is absent could be predicted via these redox discussions and equations. But it is a bit difficult to use formulas like the one that we looked at for the oxygen, for example. And the same applies to anything else. So there is really a need for something else, a graphic representation where we put up PE or E. Skipping the P would just make the numbers here slightly different, actually a factor of 17 approximately. But otherwise, the scale would be similar. pH scale is commonly accepted. This is a so-called PE-pH diagram for iron, or a predominance diagram, Medusa would have said, or a Pourbaix diagram, someone else would perhaps. We speak about Pourbaix diagram because of the a guy called Pourbaix as a family name did publish something about them for 50 years ago or something like that. Quite long time, 70 years maybe. It's nothing else than a map over an element's different states as a function of pH as well as E or P. So here, when we have such a map, it's quite easy to use it. For example, if I ask you, in a reducing environment where PE is 2 and pH is 4, weakly acidic reducing environment, what is the state of iron? Then it's just I say, now let's see if I can draw. So it's just to take this 2, make a line, and the 4, make a line, and the intersection here has the coordinates pH 4 and PE 2. And here, well, the answer to my question was iron is probably in the 2+ state. And in this case, I suppose it is aqueous also. And then you see that there seems to be some kind of limits to the map here. Up here, it is said that water decomposed to oxygen, and down here, water decomposed to hydrogen. Well, remembering what we were speaking about we have a high electron activity, a surplus of electron at low values here in PE or E. And up here we have a low electron activity. So what happens if you have a very low electron activity? What happens with the water molecule? There is a state of if we say H2O +1 oxidation state and -2. So the oxygen here is a reservoir for electrons. Oxygen is very electronegative element, so it is very eager to attract electrons. But on the other hand, if water would come to some very positive, say a positive pole in an electrolysis cell, for example, that is not at all an example of a negative environment. So then these electrons would perhaps be attracted, and the water would decompose to oxygen. And then what is the rest? If we should balance this formula, we should have 2 waters plus how many electrons? It's an oxidation plus 4 electrons and 4 hydrogen ions then. If it occurs here in the basic part, then we should perhaps get rid of these hydrogen ions. We could add 4 hydroxides to both sides. So these 4 skip to those 2, and then we have 2 water. This is a similar formula. 4 hydroxide ions goes to oxygen and 2 waters and 4 electrons. It was a bit crowded. And the same applies here. In a very electron-rich environment or a high electron activity environment, then the H plus and -2 here in oxygen, the electrons may combine together with the hydrogen, so hydrogen gas is evolved. This is a picture from some book, and of course, in principle, the lines continue outside this box. This box is called the water box, because within it, water is claimed to be stable. You can have quite basic water and quite acid water solutions, and you could have water even in quite low electron activity regions and quite high electron activity regions, but not too high and not too low. Then the actual solvent water will decompose. Let's see. For example, nitrogen has a lot of different oxidation states. Whether we have nitrate, nitrite, etc. This could be of interest because it's not so healthy, especially for children. It's used in food preparations because, for example, it gives pork meat a nice color, or at least some people think so. Nitrogen is a major component of many foodstuffs. So, for example, frying produces poisonous nitrogen-containing compounds, producing problems, perhaps. And if they are stable in water, then we could probably identify them in the four-bear diagram. Let's see, I think I have a, where here is a four-bear diagram for nitrogen. As usual, the water box, where I took this diagram from, they don't calculate these diagrams to a very large, they should have done them a little bit bigger, so the whole water box should have come into it, not cut it. Here you see that nitrate, where nitrogen is in +5 state, is actually occurring when there is a high up in the diagram, where there is an absence of electrons, while ammonium ions and ammonia, they are present in the low parts of the diagram where there is a surplus of electrons. Or at least an environment in the lower part of the water box here. The only way to come down into this lower part is that electrons are available quite freely from some other source. And I term that source just the environment. Possible questions that you can state. Suppose that you measure the pH, then you know that you're on this red line, for example. If you measure pH 6, then you measure the redox state, and if you are at a high redox state, for example here, I don't know, is it 11.5 or something like that in PE scale, then you can say that you are probably close to nitrate. That is the dominating species. This map here is not necessarily showing that it's only nitrate here. Is the concentration of ammonium ion, is it exactly 0 here, or is it only minute? Yes, and I think the answer should be the second case. So it's smaller. The dominating species is the nitrate, and vice versa. The dominating species at this point is the ammonium ion. But that doesn't mean that the other species are completely absent. Avoid stating that concentrations are 0. Absolutely. They could be close to 0. That is less risky. That is free of any risk to claim.
Yes, I was wondering a little bit why the ammonium exists in a more electron rich environment and the nitrate in a more electron poor, because I mean, maybe it's just my intuition. It seems like, you know, something with a negative charge should exist when there's a lot of electrons, but why is this?
Exactly. Good question. Oxygen is very electronegative, so that has -2 in oxidation state, and we don't have any oxygen down here, but all of the oxygens here except the oxygen gas here, oxygen in nitrate and nitrite, they also have -2, but the nitrogen 3 times -2 and minus it should be +5. And here nitrogen and hydrogen, which is the most electronegative, it's the nitrogen, so hydrogen should be +1. And here nitrogen is thus -3. So if you look at the oxidation state of nitrogen, then your question, I think, is answered. But the charge of the ion, yes, I agree that is a bit confusing. Here, here where we have a lot of electrons running around, then nitrogen -3 is in good company. And here where we don't have electrons running around, then nitrogen +5 is also stable. So that must, you need to look at the oxidation state. Otherwise,
yes, and so the I always forget the is positive more oxidized or more reduced?
Positive is oxidized.
All right,
because it's a lack of electrons, and negative is more reduced when it comes to atomic species.
Right, great, thank you.
Yeah, you're welcome. I think we have the table of nitrogen here. So the level of nitrogen oxidation, that is the oxidation number essentially, is maximum here in nitrate ion +5. It can't be more. Then you need, if you nitrogen is in column 5 in the main groups in the periodic tables. So, and it's 3 boxes to fill up until you come to noble gas configuration. So it can't be smaller than -3 either. When it comes to nitrogen, there is a very stable nitrogen compound called nitrogen gas with 0 oxidation state. And this is often not present in the Fourier diagram. If it were, then it would approximately fill up the whole water box, actually. But from practical kinetic reasons, it's quite difficult to form nitrogen gas, which is in a way lucky, because think about having an ammonium ion and a nitrate ion in a Fourier diagram where we should have nitrogen gas. Then we would have nitrogen gas here in the center, and then somewhere up here we would have nitrate ion, and somewhere down here ammonium ions and ammonia. Mixing things with large difference in redox state, this +5 and -3, this is a potential risk, because it may very well be so that electrons from the -3 nitrogen transfer to the +5 nitrogen. And then we would have this is probably an exothermic reaction, which it is, forming nitrogen, very stable gas. But this is, as I said, kinetically hindered. But otherwise, ammonium nitrate is used as an explosive. You can make a water solution of it and drill a hole in the ground and fill it with this water solution. It's completely safe to handle, fortunately. But with certain initial explosives, you can get it to detonate. And that is used. Sometimes there are accidents. The last one was in Beirut, the harbor of Beirut, for a few years ago, when there was a fire in a large storage of ammonium nitrate. Because the main use of ammonium nitrate is as a fertilizer. And this is very good, because otherwise it's less easy to find any source of nitrogen into crops. Some crops, peas, for example, they can attract nitrogen from the atmosphere, but not many. Most of them need fertilizer. Then ammonium nitrate, I think, is the main fertilizer for nitrogen. And there was a fire in Beirut Harbor in a storage room, and too large fire. So something like 2,000 ton exploded, and part of the city disappeared. This has happened several times, actually, but the last one was in Beirut. We'll see if we will see it more. We will not stop using ammonium nitrate, I think, but well, I claim that it is very safe unless you store it in large storage where and don't guard it against fire and such things. Then it
so
could
it was an exotherm reaction from
yes.
NO2 to NO3. So what happened in Beirut was the opposite then?
No, from n-3 plus n plus 5, we can draw some. You had this. You had this compound that we use as a fertilizer, and then the n minus goes to n2 then. It is actually it's not equal. I mean, the negative part here and the positive part is not, they don't cancel each other, so you need to add something else here, for example oil. Then you would get carbon dioxide and water and an explosion. This is very exothermic.
Yeah, of course. Yeah, I remembered now. Of course, it must be exotherm to give a lot of energy. Yeah.
And the problem is, well, luckily it is solid, or if it's heated in a fire, it's liquid. But if you have some mixture of some well, organic debris or something like that, then you could have very large amount of ammonium nitrate reacting simultaneously, and then you will have an explosion. Otherwise, you can try it out on lab. If you take a spoon, for example, and a small amount of ammonium nitrate, and you can ignite it, and it burns just quite as most organic compounds do. Well, this is not organic maybe, but it's similar to an organic compound in some respects. So if you want to calculate the ratio of nitrate to ammonium, for example, the 2 points here, then I think you can't do it with this diagram, except that you can predict that in point A, it would be majority of the nitrogen containing species would be nitrate. And then you can use, just find some formula and do an analytical calculation. And you need to balance the reaction. Say that you have nitrate ions that should be in equilibrium with ammonium. I use just a one directed arrow here because I don't have access easily all the time to this double equilibrium arrow, but interpret this as an equilibrium. So how to balance nitrate to ammonium? It's one nitrogen in each. Oh, that's good. Then we take the oxygens, I suggest. Free oxygen means adding free water. Now both nitrogen and oxygen is balanced. So the only thing left is hydrogen, and this is very convenient to balance because it's just to add hydrogen ions. There are 4 hydrogen, 3 times 2 is 6, 4 plus 6 is 10 on the left hand, on the right hand. So then we add 10 hydrogen ions to the left hand side. And now this thing is balanced, except charge, -1 and +10, and 1 plus on the other side. So +10 and -1, that is +9 on this side, and +1 is left. So we need to add 8 electrons on the left hand side in order to balance. So now we are ready in a way, but for the PE equation, in order to use that, we used to reduce the divide by the number of electrons. So this is actually an equivalent expression to that one. But well, we could also have 1 upon n here in front of the logarithmic part. Then we could use the second from the bottom here and essentially come to this one.
Sorry.
Yeah.
So if you write, for example, in an exercise or an exam question, that you want a balanced equation from us, then you want us to divide by the amount of electrons as well, because I'm not used to doing it, just so that I don't forget.
It's not. I will give you formulas if there will be an exam question, for example.
No, I mean the balanced equations like this. So the last line with the dividing by electrons is necessary in your opinion? You want us to do that?
Not really, actually, because if we in some text it is written that it should be this one, but in some texts it's also a 1 upon n here in front, and then one can use that one.
Okay, all right, thank you.
Because if you use that one, then you use 8 electrons, or if you would go for this bottom one, then you use 1 electron. So in both cases, one can use that one.
Okay, fine, thank you.
I'm not sure. Yeah, thank you. I'm not sure why we used some text that no one read, so we quit using that text, and that text was careful by mentioning this dividing out the electrons. But well, as I think we have. No, we don't have. I'll come back to this one. The nitrogen diagram is sort of giving an overview of the nitrogen species, except the nitrogen gas. It's very often that nitrogen gas is not present because it's difficult to produce nitrogen gas, and it's difficult to produce, for example, nitrate and ammonium from nitrogen gas. That is far from simple. You can synthesize ammonia from nitrogen in atmosphere and hydrogen gas, and then you can use this ammonia to oxidize to nitric acid and form nitrogen +5 state, and then you are immediately you can manipulate the nitrogen to nitrate ions or ammonium ions. So, but it's difficult to go directly from nitrogen gas, which is a pity, because it would be much better if the crops could actually absorb the nitrogen directly from atmosphere. You need perhaps to do some genetical modification and perhaps a lot. I'm not sure. Some crops do. So mixing in such crops like peas, some sort of peas at least, they absorb nitrogen from the atmosphere, and harvesting peas one year and harvesting some other crop another year is perhaps a possibility for agricultural production of a lot of things without so much fertilizers. But I mean, fertilizers, they are very easy to get in hand nowadays, and they're cheap. So there are no farmers that don't buy fertilizers, except those that necessarily want to stay without them. But then they get less harvest also, probably. Medusa should of course be used for drawing these diagrams. You shouldn't learn to draw them otherwise, but we'll practice a little bit about that. This is actually also valid when it comes to any other, not only fertilizers, but any other ions. When are the calcium ions free to dissolve in water? When are the sulfate ions? Where do they transform? We can actually, this is the last image, we can actually, in lecture 2, so we can actually see if we can find Medusa.
Are we going to use Medusa on the exam as well, or will we do? How will we?
I will hand out Porbet diagrams, and you just need to learn to interpret them.
All right, that's good. So if I didn't really get Medusa to work, that's no problem for the exam, basically.
No, I don't think so.
All right, that's great. Thank you.
Do you have a Macintosh or?
Yeah.
No. That's a problem, because sometimes I can't either get the Medusa to work on some Macintosh I have, because the Java version, there is not only problems with Medusa, it's also problems with the Java system. But I'll see if I can find a solution.
It's okay, as long as there's another way to find
your
answers. I am fine with that.
So we should have an electron, because we want to do an what's it called, predominance diagram or a Porbet diagram. What element are you interested in? Not iron or sulfur, maybe? Uranium. That is not uninteresting. Suppose you are a cargo company moving uranium dioxide to or hexafluoride to some factory for enhancement of the uranium grade. We can choose any one of these, and you drop the cargo in the water. What will happen? This is an old exam question. I never asked it for quite a while, for many years, but of course we reuse our exams. Uranium, run, make diagram. Here we should do predominance. And do you want this PE or do you want E?
I think E.
Hmm?
I still don't really know what a little e is. But
No. I can show you. It's is the small lowercase variant of uppercase E, but it's also other differences. But let's go to redox potential E, that is measured in volts. That's well known. Note that this 17 transforms to 1 approximately. So it's a factor of 17 in between electron activity, PE, and the redox potential. I said yes, let's see if we can get the, where is this? So it didn't show up here, but this is probably a feature in my Linux. It did show up here. So then we may make it from -2 or something like that. Or return. Then we see pH varied from 1 to 12 and E from -2 to +1.5. Total concentration of uranium is 10 to the -5. This could be changed, and then the diagram would change slightly. But how does this diagram look like? And then, since the underlying software is, yeah, here it is. This was not very nice. Let's redo it. It's a bit bad lines. Let's go to preferences. First, we should use advanced level. Run. Make a diagram. More points. 200 points in each axis will make the lines more straight, but otherwise similar. 50 is quite small number of points in each direction. And that is probably because this will take a very long time, it says here. And it did during the 60s when the first software were actually written, in the end of the 60s and the beginning of the 70s. But yeah, nowadays computers are way much faster, so we are already halfway through, and my computer is 10 years old or something like that, and it should be running quite fast on a modern machine, but even this is quite fast. Now let's see. It calculates actually in a matrix of 200 by 200 points, and then divides thing here. Here is the uranium diagram. Between these two green hashed lines, the water box is present. So if you drop a cargo with uranium fluoride in the sea, which has happened actually, but luckily uranium is very expensive. So I think every time that has happened, there has been a pickup with from some other ship. If it sinks to the bottom of the sea, where we can expect high electron activity or reducing environment, we could perhaps have uranium dioxide. It's up to here, or slightly more oxidized uranium oxide, or up close to the surface where we have a lot of oxygen. Then we would have some other, what is the oxidation state here of the different types of uranium? Well, here it's +4. 4 and 9, this is difficult because oxygen should be -2. Then the uranium should be plus 4 times 2 divided by 9. Or am I? No, sorry. I am completely wrong. 9 times minus 2 is minus 18 for oxygen. Then the 4 different uranium should also be 4 times something should be plus 18. So uranium is 18 upon 4, which is 4.5. Strange oxidation state. And if we want to go to integers, we can say that we have 2 times uranium 4 and 2 times uranium 5. So compared to uranium 4 plus, only a few of them have been oxidized, or we can say on average they have been oxidized half a step. Here then, OH is -1. It's an ion that you know of -1. So the whole ion represent -1, and it's 2 of them. The oxo represent -2 each. So here the uranium metal or the uranium atom should be 6. That fits. 4, 4.5, 6. I mean, the steps are not equal, but it is at least more oxidized up here and less oxidized down here. Similar to the fact that species in acid environments or species in basic environment, they are different in the respect that either the acidus species, they should contain more or a larger number of hydrogen ions. This is not visible here, but less number of hydroxides than the one present at the basic environment. Down here you see the uranium metal. Why don't you see uranium metal very often? Or hardly ever. It's only occurring in very few nuclear reactors actually use uranium metal. Most of them use uranium dioxide or this oxide. These two are very stable and high melting, and they are stable in water. That is maybe important. If you drop a piece of uranium metal, then that's not exactly, but close to dropping a piece of sodium metal in water, which is disaster, because then it is destroyed. You don't drop uranium metal normally in water. That has never happened, I think.
I was thinking, you have here, or in these diagrams that we've been looking at, we have the water box, but what is the typical spectra that you'd find water? What reduction potentials would you find in like the environments?
You find you find the typical, maybe not, maybe most here, because you don't. Most normal waters they are a little bit acidus or a little bit alkaline, but not very, approximately neutral.
Yeah.
And then the oxygen gas is the main agent that makes the potential quite high. You could see this if you should be down here, for example, in the at the lower part of the water box, then you need to have some reducing agent or very, very low oxygen levels, which is, for example, possible at the bottom of a deep lake or sea, or in some deep down in the ground where there is a lot of organic material. We can look at organic diagram instead of uranium.
All right, but so it can go all the way up to the top and bottom of the water box.
Yes.
In a
yes.
lake, but it depends on what part of the water you're in.
Yeah, exactly.
Okay.
So now I'm calculating the carbon diagram. Oh, sorry, I forgot to change this number of points. But here there should be a small area here. We can. What is the color of carbon? It's brown. So it's a small piece of elemental carbon in this area. Up here is carbon +4, and down here is carbon -4, with carbon 0 in between here. This is perhaps a good view of the natural waters. They could be somewhere in this area, except at the bottom where they are in equilibrium with the organic matter, whether it is carbon 0 or whether it is less, even more reduced carbon. So many carbon compounds could be said to have negative. I mean, this oxidation state is not a real quantity. It's just something that we use for balancing formulas. And the concept it does not correspond to charge, at least not very good. Slightly, it's not without a relation to the charge of the atom, but not a lot. But I mean, this diagram is calculated from experimental data. So in an acid environment with access to air, oxygen, you have carbonic acid. And in a basic environment, you have the same oxidation state of carbon, but it just loses the hydrogens. But in most waters, it behaves like hydrogen carbonate. And hydrogen carbonate is stable at very many oxidation levels.
Seeing this, I have a question.
Yeah.
So, for example, in sediments, you do find, like you do not find it because you can't see it, but according to what I remember from my microbiology lecture, CH4, so methane is definitely something occurring in the environment.
Yes.
And more commonly than, like, for example, in the sediments of some kind of a lake out there, you wouldn't find elemental or crystalline carbon, so not coal or whatever. Is there some kind of kinetic barrier, or what's going on?
Yes, this is probably a kinetic barrier, exactly, because I mean this elemental carbon. There are several reasons. This is a diagram calculated from species that are known to exist in equilibrium. So if there are some kinetics involved in the transformation between these species, it's not visible here. On the other hand, also note that this is a calculated compound or calculated diagram, and if we don't know equilibrium constants, or if we have wrong equilibrium constants, then it will look weird. We could, for example, if we modify the chemical system, so we don't want any methane, we don't like methane, lead complex. Yes, yes, and we don't like the dissolved methane either. I mean, don't like is absolutely non-scientific, but sometimes that's actually used. Yes, it's slightly better. So here is the same carbon diagram, but we have avoided the methane containing species. So let's see what happens then. Then the area where the elemental carbon is present got a larger part of the diagram, and then we get methanol down here instead. Perhaps this is a better representation for reality, or perhaps a worse. Do we know, is there methane? You said it was methane, and it is. I mean, in deep sea sediments, for example, quite far down, a kilometer or so, there is a lot of methane present in the ocean floor. Maybe more methane actually than the rest of the carbon sources in oil and solid carbon, because there has been a lot of long time with the organic carbon filling up the ocean floor, and what does happen? Yeah, maybe it transforms to methane or methanol. The carbon in methanol and carbon in methane, they are approximately similar from a redox point of view.
But I'm sorry, I was writing what was changed for this diagram? What parameters?
I deliberately deleted the presence of methane.
Ah, yeah, okay.
To emphasize that the diagrams, they are constructed from what we know and from the constants that we know. Maybe if we go down in the sea and do some analysis, we find methane, and this is not present from the Pourbaix diagram. So where does it come from? Well, it's simply because we were missing some theory, some equilibrium constant. We did not suspect that methane should be present. Then we go back to the lab and determine equilibrium constants and reconstruct it, and then we will get methane instead, or methanol here. And this elemental carbon will be much less, a smaller area. But I mean, look at the general trend in oxidation state. You have carbon +4 and here you have carbon 0. So more reduced carbon down here. And what kind of species, if it is carbons, elemental carbon, or whether it is organic compounds, probably if you look at the sediments in a lake, there are hundreds of thousands of organic compounds that are quite appreciable concentrations. But then it becomes more or less impossible to take all of those into account, because the diagram would look completely weird, just like a fly swarm or something like that, with a lot of compounds. Sorry, time runs 10:57. We need a break, I think. Is 13 minutes okay? To 10 past?
Yep.
Then I